Thank you very much for the introduction and welcome to the last talk of today. I'm very well aware that standing in the way of an early dinner and a nice evening, so it's a pretty hard proposition, and I'm standing here with a technical talk. So I'm trying to make it as pain-free as possible. My pain tolerance is pretty high though, so your mileage may vary. But let's not waste any time and get going. So I've just spent like the better part of half a year making type inference better for 1.21, and so this talk is about type inference as it relates to Go. And by the end of this talk, I hope you understand a little bit better how it works, and maybe it helps you understand some situations in your code that may be mysterious or don't work as they should. So let's start with the terminology. Wikipedia defines type inference as follows. So the key phrases here are automatically deduce the type of an expression without explicit type annotations, or simply determining the type of an expression automatically. Go had a basic form of type inference from the beginning. The types of constants and variables are automatically determined or inferred if they are omitted in type declarations which have an initialization expression. And so the types of those variables and constants are simply the types of the expressions on the right-hand side of those declarations. The effect of leaving away types is most pronounced in short variable declarations. Such a declaration combines type inference and a little bit of syntactic sugar, the ability to leave away the var keyword, and combines this into one very compact statement. And being able to leave away the type in the variable declaration removes repetition, or stutter as some people like to call it, and at the end increases the readability of the code. So with generic code, we have the potential to significantly increase the amount of types that appear in the code. And without type inference, each generic function and each type instantiation requires type arguments. And being able to leave them away becomes even more important. Here's an example that's using the new slices package used without type inference. Highlighted in red are the explicit type arguments that need to be passed to sort and binary search. And of course, we would prefer not to have to write those. The same code without type inference is clearer, cleaner, and more compact. In fact, it looks exactly like non-generic code, and that is the point. Type inference makes this possible. Importantly, this is an optional mechanism. If type arguments make code clearer to read, by all means, write them down. So before I continue, let me introduce some notation I'll be using in some of the slides, just so they become a little bit clearer. Most of these symbols are hopefully self-explanatory once you see them in context. For people who are perhaps new to Go, under of t means the underlying type of a defined type. So if you give a type a name, the underlying type is usually what's on the right-hand side of that declaration. It's usually a type literal, something that's unnamed. I'm using this slanted fat t here to denote the type of an expression. I'm using this triple equal sign to express that the two sides on the left and the right have to be equal or identical. The double arrow means implies, of course, and then the single arrow means that what's on the left-hand side is a type parameter, and it's inferred to have the type t, which is on the right-hand side. So with that out of the way, let's get back to our previous example. Inference compares type patterns, where a type pattern is essentially a Go type which contains type parameters, and sometimes we also call those type variables because we have to find values for them, type values. Type pattern matching allows us to infer the types that need to go into these type variables. So in this sort function call here, we pass a list variable as a function argument for the parameter x, pointing this out here with these two purple dots. So list is going to be an argument for the parameter x. Therefore, the type of list, which is the capital list, must match the type of x, which is a type parameter, s in this case. And so if s has the type capital list, then this assignment becomes valid. In reality, the rules for assignment are more complicated, but for now it's good enough to assume that these types just must be identical, expressed here with the is identical to operator. Once we have inferred that the type of s is capital list, we can look at the type constraint for s. And the type constraint for s says that the underlying type of s must be slice of e. The tilde here in the type constraint means the underlying type. So we know that the underlying type of s is slice of int, and therefore we know that slice of int must match slice of e, and therefore we can infer that e in fact must be int. And so now we've been able to infer both the types for s and e such that these two types match, and inference has succeeded. We don't need to write it down. So let's look again at pattern matching. Here's a more complicated scenario where we have a lot of type parameters. We have s1, e1, s2, e2 from equal func, and then we have again e1 and e2 from the equal function, and all of them sort of flow into the slices.equalfunc call. And so we have a total of 6 type parameters. So this is a place where type inference really can shine, because there's a potential to potentially leave away 6 type arguments. And the type pattern matching here still works, but we can see how it may get complicated very quickly. And so we need a somewhat systematic approach to determine which type parameters and which types get involved with which patterns. And so it helps to look at type inference in a slightly different way. We can see type inference as a problem of solving type equations. And solving equations is something we are all very familiar from high school algebra. And if that raises any bad memories for you, don't worry. I promise this is going to be a whole lot easier. This gopher, for sure, is very excited about these equations. So the variables in type equations are the type parameters. Solving the equations means finding values, that is, type arguments that make these equations true. And this view makes the whole type inference problem much more tractable, because now we have a formal framework to think about it, to write down the information that flows into these into the inference, and hopefully come up with an algorithm, deduce an algorithm. Our earlier example can now be reformulated as a problem of solving type equations. And here the triple equal sign again stands for is identical to. So now that we have these type equations, it's time to look more closely at the possible type relations. So far we have simply talked about types having to be identical, but in actual Go code that is too strong of a requirement. In our example, S must not be simply identical to list. It's rather that list must be assignable to S. And similarly, S must satisfy its constraint. And we can express the actual type relationships with different type relations, here expressed as this identity relation with various subscripts. I apologize for the subscripts, I just couldn't find better symbols, so hopefully you can read them. Altogether, we have 3 different kinds of relations. Either 2 types, x and y must be identical, or y must be assignable to x, or x must satisfy the constraint y. We also need to determine where the type equations are coming from. In other words, we need to identify what code contributes which equations. And in a generic function call, we may have explicit type arguments. For most of the time, we hope that we can infer them. And typically, we also have ordinary function arguments. Each explicit type argument provides a trivial type equation. The type parameter must simply be the type argument because the code says so. Each ordinary function argument contributes another type equation. And finally, each constraint for all the parameters for all the type parameters involved also provide additional information. And this produces, a certain number of type parameters and type equations. These numbers don't have to be necessarily the same, so that's where it's a little bit different than high school algebra. So for instance, in this map example, where we have two type parameters k and v, we have only one equation, but we actually can infer two types at the same time. So let's look at these three kinds of relations or these three kinds of situations in turn. If a type argument is given explicitly, there's really nothing to do. We can still write down the respective type equation if we care for completeness, but in this case, the Go compiler simply substitutes the type argument throughout all the type equations, and the variables, the type parameters disappear, and we can forget about them. But when we have an argument, say x, which is passed to a generic function parameter v, or when a generic function x is assigned to a variable v, the type of x must be assignable to the type of the parameter v or variable v. And we can express this with a suitable type equation. Note that if neither v nor x contains any type parameters, the equation is either true because the assignment is valid Go code, or it is wrong, it's false because the code is invalid. This is no different, this is just ordinary Go code that's not generic. So there's no type variable to solve for. And for this reason, type inference only considers types that contain type parameters of the involved functions. So finally, for each type parameter for which we want to infer a type, there's also a constraint, and we can extract the type equation from its constraint. What that exactly looks like, we're going to see in a little bit. In Go 118, inferred parameters had to be all for the same function call. Specifically, it was not possible to pass a generic uninstantiated function to a generic function as an argument, or assign such a generic function to a function typed variable. In Go 121, that has changed, and type inference is quite a bit more powerful. It now works also in these cases. Now type parameters can come from multiple functions, as in this example here, where compact func the compact func call requires the inference of both s and e from compact func, but then also the type parameter p from my equal. And so with multiple functions involved, type equations may also be from or involve more than one function. And so in this case, the compact func example, we end up with 3 type parameters and 5 type equations. The solution here is still pretty easy to see for humans, but this example gives another idea how things can get very complicated fairly quickly, especially if the types that are involved are more complex. So far we talked about the various sources of type equations, but we've not been very precise about which type parameters to solve equations for. Let's consider another simple example. Here we have a sorted print function that calls slices.sort to sort the incoming list. Both of these functions are generic. We want to infer the type argument for the sort call. The type equation for the parameter passing here is slice of f, must be assignable to s. But in this equation, we have 2 type parameters, so s and f. Which one do we need to solve the type equation for? Because the invoked function is sort, we actually care about its type parameter s, not the type parameter f. We say that s is bound to sort because sort declares s, and s is the function. Sort is the function that we are involving and calling here. F is bound to and declared by sorted print. But we don't care about that here because we're not going to call sorted print. And we say that f is free with respect to the sort call. In fact, f already has a type. It's whatever that type f is. In some ways, it is a constant. So when solving type equations, we always solve for the type parameters bound to the function that we are going to call. Now that we have established how we collect all the relevant type parameters and type equations, we need to determine how to actually solve the equations. And so by now that's probably become obvious that solving a type equation actually just means comparing two types x and y against each other, and in the process determine the type arguments for any of the type parameters in those equations such that the two sides become equal. So if we see a type parameter for the first time and is matched against another type that is not a type parameter, then we just set the type parameter to that other type. If a type parameter has been seen before and already has a type argument inferred for it, then that type parameter stands for that type. And finally, if two type parameters match against each other and neither of them has a type argument inferred for it yet, then they are unified, they are joined. That means that going forward, they both stand for the same type parameter, type argument. If one of them gets inferred, the other one gets the same type inferred for it. And so this kind of unification is the central operation here, even though in practice this situation is actually relatively rare. In fact, before Go 121, this was actually not even, this never happened. We simply call the entire process of matching types unification. So this sounds all pretty complicated and dry, but hopefully it will become a lot clearer with a concrete example. So let's look at these two types, x and y, and let's assume that these two types have to somehow become identical. And we need to figure out what are the values of the type parameters a, b, and c. So we start at the top and recursively walk down this type tree. For the two types to become identical, they have to be, all the pieces of these two types have to be identical. And so at the top we have both times a map type, so that's good. And we can continue down to the key of these maps. And so now we have a type parameter a, which is matched against the string. A doesn't have a type inferred for it yet, and so therefore we can now infer a must be string. We continue on the value side. We have two structs. They are the same, so that's great. We see the field type of one of the fields of these structs. Here we have a type parameter c on the right-hand side and an int on the left-hand side. So they must be the same, so that means c must be an int, and so forth, all the way to the bottom. And at the end of this recursive comparison, we have, in fact, figured out all the values for the type parameters a, b, and c. And so we have a success. So now let's consider a slight variation of this previous example. Here, x and y don't have the same type structure. So again, start at the top. We have two maps. It's all great. Go down on the left-hand side. We have a and the string. And these two guys must unify. So we know a must be a string. But now we match a struct against a bool. These are two different types. They cannot be made the same, and unification fails. So that's a case where your code cannot be, this equation cannot be made true. If this appears in code, there's no type argument that satisfies this, and your code cannot be, even if you would provide explicit type arguments, your code cannot be made to work. Here another example where we have the same type parameter appearing twice on the left-hand side and on the right-hand side. So we have a twice on the left-hand side and c twice on the right-hand side. Again, same situation. We start walking from the top. We know that a must be string. We compare two structs. They are identical types. We look at the field types. We know that c must be an int. We continue down the road. And now we see a and c matched against each other. Now, both A and C, they have already a type inferred for them, so they are standing for that type. And a string is not an int, so these are in conflict. This equation cannot be made true, and we have a failure. So hopefully this gives you a little bit of an idea how this process works. This is what the compiler does when it sort of does type inference for a simple situation like this. So unification solves type equations of the form where x must be identical to the other side, to y. But what if the relation is a different one? What if we want to have unification for assignability, or when we have satisfiability for a constraint? And so the following situation helps us in this case. Type inference is actually only one small step. It is not the same as type instantiation, and it's not the same as calling a function. And type inference simply gives us hopefully good type arguments. They may be wrong. Instantiation is still necessary afterwards to check whether the type arguments that were inferred actually satisfy the constraints. And checking whether all the function parameters that are being passed actually are assignable to the corresponding function parameters is also an extra step, and that may fail as well. So if type inference is not precise enough, it may not necessarily infer a correct type. It may in fact infer a type where no type exists. But if that is the case, that is okay, because we have still two steps, number 2 and number 3 here, that are being executed after type inference, and they may fail. So either way, the compiler will produce an error message, whether it fails at type inference or later, and it's just that this error message may be slightly different. Most of the time, actually, we won't notice. So with that observation in mind, we can now go about simplifying some of the other relations. So if we want to unify for assignability, we can actually make certain simplifications. Go's assignability rules are actually quite complicated. We don't really want to sort of embed them in the unification process. We are actually good as long as we can find potential type arguments. We're happy, we're just going to continue because type inference is still followed by type instantiation and function invocation. So if inference finds a type argument where it shouldn't, we will fail later. So when we match for assignability, we do a few simplifications. We ignore channel directions. And if a defined type, that's a type with a name, is matched against the type literal, we instead look at the underlying types. What that means, we'll just see it in an example shortly. And finally, if we are matching against an interface, then the types may not be the same at all. You have like a concrete type and an interface. So we accept any type that has all the methods of the interface and where all the signatures match. And with these simplifications, we can actually use the same algorithm as before and essentially look for identity, except with some variation at the top level of a type. So let's look at this in a concrete case. Let's assume we have our list type from before, and we want to assign it to a parameter that has the type slice of E. So we again try the unification here, and list and slice of E, they are different types. If we don't do anything here, unification would fail right away. But because we are inferring or unifying for the assignability relation, we, in this case, continue with the underlying type of list. And now we continue with this. Now we have two slice types. They match. We can continue down the road. We see an element type int and an element type E, and with that we can infer that E must in fact be int. And so we have success. So if this were to infer an incorrect type argument for E because of the simplification, we would fail afterwards, because if the type of the variable or the expression that we're going to pass to the parameter of type slice of e is not assignable, that will be caught. And similarly, we can make simplifications for constraints. The constraint satisfaction is even more complicated than assignability, and so it's really important that we sort of can make that manageable. And again, constraint satisfaction is checked at instantiation time. So the goal here is to help type inference where we can. It's not absolutely necessary that we use all the information. And so this is typically situations where the constraint is relatively simple, where the constraint says this type must have a certain structure. For instance, it must be a slice, or it must be a map, or things like that, or it must be a pointer. And so these are situations where the constraint has what in the spec is called a core type, which, roughly speaking, means that all the types that satisfy the constraint have a certain shape, such as slice of E. And so therefore, constraint satisfaction, this part of inference, only looks at constraints that have a core type. And then we can again use the same unification mechanism that we use for identity. So now we have seen how type inference works by solving type equations with unification. But what if there are no types? What if the function arguments are untyped constants? So for type inference, typed arguments always take precedence because there is a given type and we want that type to have, the final say. Only if a type parameter doesn't have an inferred type for it, and only if it must match against an untyped constant, is that untyped constant is considered. Let's consider a function foo here, which takes an arbitrary number of type arguments. Sorry, an arbitrary number of arguments, and they must all be of the same type p. In the first three function calls here, we pass a variable of type x, a variable x of type int, together with no or one constant. And so in these cases, the constants are actually completely ignored. Type inference looks at x only. It infers that p must be int. And then the call proceeds as if it was instantiated with int. So untyped constants here are ignored, and we have the usual conversion. So 2.0 is being converted to an integer. That works. The 2.1 cannot be converted to an integer, and so this is going to lead to a failure, compile time failure. But it gets more interesting with the last three calls to foo. Here the arguments are all untyped constants. There's no given type here, and that we can use for inference. Now type inference must look at the constant's default types. And here is a quick reminder what Go's default types are. We have 6 different kinds of constant types. We have booleans, integers, runes. We have floating point values, complex values, and strings. And we have corresponding default types. And in some cases, when different numeric constant kinds are matched together or mixed up together in the same expression, then we choose the default type that is later in this list. So going back to our foo call, in Go 120, if different default types needed to match against the same type parameter, we actually failed. Inference failed. We said there's an error in the program. And this was not very ergonomic to use, and it was also different from how constant expressions work. If you say 1 plus 2.3, then the result is actually a floating point constant and not an error. And so we want to do the same for type inference, and so in Go 121 this is fixed. If multiple untyped constants match against the same type parameter and it's numeric constants, then we choose the default type that is later in that list that we've seen here for the type. So now we've sort of got the big picture about type inference, but there are a couple of special cases that I haven't talked about, and they're they're making things slightly more complicated. So the first one has to do with the order of parameters when you pass them to functions. Independent of that order, we should always get the same result for type inference. So independent of the order in which parameters are passed to a function, or in which case, the parameters are permutated, we want to see the same result. So let's look again at our foo function here. The type inferred for p should be the same whether we pass s or t afterwards, or whether we pass t first and then s afterwards. So in both cases, we want this function to print, the type t. But unfortunately, our algorithm as described so far doesn't do that. And the problem is seen pretty quickly here. Depending on the order in which the unification solves the two equations, we actually arrive at different results. In this unification order on the left-hand side, number 1, the first type that is matched against the type parameter p is a struct. So we infer p must be struct, an unnamed struct literal. When we then later see the type t, because we unify for assignability, we look at the underlying type of t. The underlying type of t is struct. We compare struct against the struct. Everything is happy. And type inference succeeds. And the result is p must be struct. On the other side, if we look at order number 2 here, if we first match against t, then we infer p must be t. And now, if we now see the struct type, we again have struct matching against t. We are unifying for assignability, so we look at the underlying type of t. We have struct matching against struct. Everything is happy. Type inference succeeds, but now we infer the type t. And so that is not good. Luckily, this is a fairly easy problem to fix. If we have a situation like this where we inferred a named type for a type parameter, and later, if we have a situation where we infer an unnamed type for a type parameter, and later we find a named type that also matches because we are unifying for assignability, then we correct the type parameter to the named type. And so it doesn't matter how many times we see a type literal and then a named type, as long as they match, the underlying types match, we always end up at the same name type at the end. If we see multiple name types, then they are either all the same or they're different, and then we fail. We made similar simplifications for channels and interfaces, and they require similar corrections. I'm not going to talk about those here. So if we look at our earlier example again, we can now see on the left-hand side here in the unification order 1, if we proceed with the struct type first, we infer p must be a struct. Now we get to the t, and everything is fine, but we know that p is a literal, not a named type, and we just matched against the named type, so we correct it to the named type. And if we follow the other unification order, the other order of the equations, nothing has changed, so everything is like before. But the important thing here is that now in both cases, independent of order, we infer the same type t for the type parameter p. So everything is happy. Another interesting scenario is self-recursive types, functions. Let's consider this generic factorial function that I've sort of changed a little bit so that it also works for floating point numbers. And note this is not a mathematically correct implementation. It just needs to recurse. And also, the point here is not that this is a factorial function, but just that the fact calls itself with its own type argument. Okay, and so in this situation, the type parameter p is simultaneously a bound and a free type parameter, or in other words, a type variable and a type constant. And if we write down the corresponding type equation using the same mechanism, the same, sort of approach that I've described so far, we end up with an equation where P must be assignable to P, or, P must be identical to P. And both times we have a type parameter, there's no information, we cannot solve this. And actually type inference will fail. Even though, for us it's trivial to see that, in fact, the type argument here is just P. And so, luckily, this is another problem that's fairly easy to fix. Before type inference is invoked, the compiler simply renames the type parameters in the signatures of all functions involved in the respective calls. And so the effect of this renaming is the same as if we had introduced the helper function. And so with the renaming, or with this helper function, the P that needs to be inferred on line 7 is a different one than the one that is declared on line 3, because we did the renaming. Or with the helper function, as in this case, this P is now Q. And so now the equation looks different. Now we have we have P must be assignable to Q. And now we can infer that in fact Q must be P. And remember, this Q is the type parameter here of the helper function. So if we instantiate helper here with P, we in fact get the correct result. Okay, so we've come to the end, and so at this point the question is, what is missing? And I think the most glaring feature that I haven't talked about at all is type inference for type instantiations. And in fact, Go doesn't allow this currently. This is only a problem if you have more than one type parameter for a generic type, because we have to write at least one type parameter down, because it's not a function call, we don't have any other arguments to go from for inference. And so this is a relatively rare situation. Closely related to that is type parameter declarations that are sort of cyclic in nature, like the second example here. And both of these cases can lead to very, very complicated cycle problems for which we don't have a good handle yet. We don't really know how to solve them. But we can solve them for some important cases, namely when there's no obvious cycle. So stay tuned. And finally, there are situations where type inference is simply not strong enough. Okay? We believe that such cases are pretty rare at this point, or unimportant for real code, and that our implementation as it is right now covers the large majority of all useful code scenarios. But if you run into a situation where you believe type inference went astray, or it should have solved the situation and it didn't, please file an issue. As always, the Go team loves to hear from you, and especially when it helps us making Go even better.